All right, welcome. In this video, I'll show how to find a parametric description of a helicoid. So before I can really start in that, I want to give a geometric picture of what the helicoid is. Here we go. It's sort of, think spiral staircase. So, they can extend vertically up and down forever as you'd like, but for today, we'll just kind of let it be one single rotation. Okay, so what it is think spiral staircase. It's sort of something like this. And as we go up, we rotate out. So that's kind of like the skeleton, and let me show what's happening. Something like this. Okay. Something like that. Okay. This is in 3D space, and it's a surface, right? It looks like a two-dimensional object sitting in 3D. So we have a chance at coming up with a parametrization of the object. All right. And remember, a parametrization of a surface is merely an x of uv, a y of uv, and a z of uv. This describes a surface. So let me show you one way you can kind of break this purple shape down, this helicoid, into smaller components, and maybe find an easier way to find a parameterization, this down here. Because it might be helpful to, I don't know, maybe you want to compute the area of that thing, maybe you want to compute some sort of, maybe that's modeling the surface of a screw. Maybe you're an engineer and you want to use the best kind of screw to go into your piece of furniture, and a helicoid might be a pretty good model of what that screw might look like. All right, so let's move over here. I want to kind of break down one way to look at a helicoid. So all right, here's my vertical axis that will kind of be spinning around, and one thing to notice is that at each height, so I've got a collection of heights. Maybe this is at z equals 0, and this is my top z value. I'm going to cut it in half a couple times, half, 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 and I'm going to cut those segments into halves. 1, 2, 3, 4. Okay, so I've kind of cut the thing into eighths. And what you notice is it's kind of like a pine tree. This is the vertical core of your pine tree, and outwardly extending from that center are branches, and these are horizontal rays. So at the base, when z equals 0, we're kind of going out to the far right. Okay. And up at the top, we'll also be going out at the far right, okay? But these branches do a twist as you go from bottom to top. There's a rotation. So halfway along this Z, which is this sort of dot that I've drawn in that center, our branch will be moving out, extending towards the left, right? Kind of, oh no, that's too thin. Going out to the left. And on all these three spots in between, we have some sort of twisting to get from the left to the right. Really, I'm drawing that thing right there. So the thing you're seeing is that vertical chunk, that right piece, this left piece, and this right piece. Okay, so to kind of fill in the bits, I've got another ray coming out here. And let's say that's half, we're kind of doing this in halves, or quarters, I suppose. So a nice thing to do is look at the projection down to the XY plane that's sitting beneath. One thing you might want to do is for each ray, you can sort of geometrically describe it by the angle it makes with that positive x-axis. That's this one down here. I'll do it thick. That thing. Mathematicians who do coordinate geometry really like to measure their angles from that positive x-axis down there, positive x. So let's kind of go up the list on each of these branches and see what the theta value is. So I'm going to say that the angle formed by the branch, which is the ray, with positive x-axis, let's call that theta. Okay, that should make sense if you've studied polar coordinates. All right, so at this ray right here, we've got theta equals 0, right? Oh goodness, right? That ray at the bottom is precisely the positive x-axis. Now you bump it up a little bit. I'll draw a reference frame. That's x. This is y. We're right in between that positive x, positive y. Makes a 45-degree angle with that positive x, but 45 we know is theta equals pi over 4. So really the idea is you should see that each branch, as you jump up in z values, you're also jumping up in theta values. So as you're lifting, as you're rising from the ground, from the earthy ground, your branches' theta values are increasing. So both z and theta are increasing. So all right, let's compare again. At this point right here, that's a perfect 90-degree angle. So there we've got our theta is pi halves. Up here, let's do the graph. Well, that's kind of halfway in between. Here. That's this thing right here. This branch over here, this next one up is 3 pi fourths. It's making a 135-degree angle. I'll kind of project it down here. This is the one I'm considering. And if you draw it down here, this truly is a 135-degree angle. That's the theta we're measuring. So this one gets theta equals 3 pi fourths. And up here, I'm going to write that ray is theta equals pi. You can see how this process will continue as we go up higher. So to find a parameterization of the full surface, this full thing over here, it might be nice to think of that corresponding z theta value as fixed, and just to describe that ray. So think of fixing a certain ray that is equivalent to picking a height or picking a theta value, same thing, and describing that ray. So I'm going to describe this parameter. So note that the height and the theta value of each ray, and when I say ray, I mean that an outwardly extending pine tree branch is what I mean, that each height and theta can be described with a single parameter. So note that the height and the theta value of each ray may be described as a single, with, get my English right, with a single parameter. Let's call this u. Okay, so what I mean by this is if you give me a u value, a u between 0 and 2 pi, I'll tell you the branch we're talking about. So you tell me something like, let's talk about 2 pi thirds. So example, if you tell me u equals 2 pi thirds, I can already tell you what branch I'm talking about. I'm talking about the branch that happens up here. Nope, if that's halfway through, then this might be 2/3 of pi, and it's kind of coming out this way. So the height and that angle are both 2 pi thirds, 2 pi thirds. So in a sense, the u is parametrizing which ray you are on. Okay, so now that we've, for example, fixed in our minds a u value, so in our minds, fix a u value, how do we describe the ray? How do we describe the ray using a single parameter v? So back to this boxed example, if for a fixed u, the thing I'm trying to explain, the thing I'm trying to describe is this purple ray. It's a one-dimensional thing, and it is a one-dimensional object, so it needs only one parameter to be described. So how do we describe a purple ray with after we've kind of in our brains fixed a u, so our u is fixed? Okay, so I just want to remind you that you've done this, at least in my multivariable calculus class, we've done this a bunch of times. We know how to parameterize lines. To parameterize a line or array or a line segment, what you need is a base point and a tangent vector. So we need a base point and a tangent vector. So going back up here, what I was saying up here, this height and this theta, both of these are described with u. So what I'm saying is z equals u and u equals theta. Okay, so if we fixed a u value, looking up at the top, that means we've also fixed a z. So when I'm trying to describe this ray, I'm looking at my base point, and a good base point to start at is 0, 0, u. So our base point is 0, 0, u. Remember, we're thinking about u as fixed. We're pretending u is fixed. So if you really want to stick to something, pick u equals 2 pi thirds, and that would be your z coordinate. That's how high up you are. So that's one piece of the parameterization for the ray. We've got a base point, we need a tangent vector. Now a tangent vector is going to be, I'll kind of draw it in that picture. A tangent vector is going to be sitting in that horizontal z equals u plane. And to describe it, I just need like the displacement vector. So really, I'm starting at that central point, that kind of like that origin in that horizontal plane, and I'm displacing to a point on the unit circle. And that value on the unit circle is characterized by its angle. And that angle from that x equals that positive x-axis is also equal to u. So that location, this tangent vector is a displacement vector from 0, 0 up to that location on the unit circle. And a unit circle is cosine sine of the angle. I know that my displacement vector should be cosine of u, sine of u, u minus my base point, which was 0, 0, u. That's how you get a displacement vector. It's final minus initial. And if you do that subtraction, that z coordinate vanishes, you get cancellation, and you're looking at a cosine of u, sine of u, 0. So what have we found? To reiterate, we're trying to find the parameterization of that purple ray. And what do we have? We have a base point. I'll highlight the base point in yellow. And we have a tangent vector highlighted in blue. If you give me a base point, and a tangent vector, I can tell you how to parameterize the ray through those two things. Okay, I'm going to this next page. So that means I'm going to write, so thus, the parameterization parametrization of the ray through my base point 0, 0, u, which is along or tangent to cosine of u sine of u 0 is, okay, I'm going to use a t variable for a second. I'm going to flip it to v later, but I'm going to use a t variable to just remind you how we've done this a million times previously in this semester when we use a t variable to describe a curve. So I've got r of t is 0, 0, u plus t times cosine u sine u 0. And if I put this all together, this just gives me t cosine u, t sine u, comma u. And this describes that purple ray coming out of that vertical z-axis. And I don't really like using a t, I really like using a v. So if I just replace my t with a v, totally artificially, what I get is, in fact, it's an r of uv. So all I'm going to do is I'm going to change out t equals v. That should be a v. All right, t equals v. I've got b cosine u b sine u comma u. Okay, and this I claim is the parameter. This gives you the parameterization of the helicoid. And I can really geometrically tell you what the u and the v are telling me. The u is telling me, the u tells me which ray I am on. U tells us which ray we are on. And V is telling us how far along the ray we are. V tells us, remember V is like T, and T tells you how far along you are on your line or your line segment or your ray, and V is just that T, so V is playing that role. V is telling us how outwards we are, and U is telling us which ray we are on. So V tells us, V tells us how far along that ray we are on. And there you go. That is your parameterization of the helicoid surface. And I suppose you probably want, well, I guess you can let your U's and V's do all sorts of crazy things. You probably want your V to start off at 0. So I'll let your V start off at 0, and maybe you'll go off to infinity. So that parameter domain will be an infinitely outwardly stretching helicoid. If you wanted to truncate the edges so it actually looked like a physical screw, you might take V to be 0 to +1, and that would really cut the edges so you had a finite thing. And also your U, you could truncate however you'd like. So if you wanted, so I'll go to this next page. I'll do an example. So what I mean by this is you can have V go from 0 to infinity, and you could have U go from 0, sorry. If you had U range from negative infinity to infinity, what you would have is something that went upwards forever, downwards forever, and you'd be extending, your fibers would be going out forever. So that's the picture you get for those bounds. But let's say you wanted V between 0 and 1, and let's say you wanted U between 0 and 2 pi. This would give you a finite shape. You'd stop at the lowest value of 0 and the highest value of 2 pi. And your rays would only go out for length 1. And this is the shape you would get with these edges. That's the edged shape you would get. All right. So you can have more fun playing around with different U and V bounds and seeing how that would affect this shape. It's a pretty good exercise if you want to fully understand the parameterization that we've developed. All right. Well, I hope that was useful, and yeah, keep doing calculus.